Okay, welcome back from Thanksgiving break. Raise your hand if you didn't do any work over Thanksgiving break. Yay, good for you. I didn't either, so. But on that note, your projects should be wrapping up soon. So you've got a few weeks before final presentations. Those are going to be on December 11th, and it's going to be in the style of science fair. So we're going to put you in the atrium, and you're going to have your own table, and all of your team members are going to be there. And you're going to explain to whoever comes by what your project is about and how you went about building it. So me and Vivek and other staff members will go around and talk to you. So make sure if you're like sort of quiet or you don't know what's going on with your project that you get up to speed before then, because we do target like quiet people and make them explain things. But yeah, just know what's going on with everything. Make sure you wrap everything up before then. So anything that you need to finish, if you have some things built but they're not actually put together, make sure you take some time to do that. So if you want your PM to sit with you for a couple hours and work on that, they can't write the code for you, but they can sit and help you make sure everything gets finished up. Please go ahead and do that. Okay, are there any questions about final presentations or grading for that? Yeah. When is it? Yeah. December 11th. So it's just the Tuesday before the week of reading day. Sorry, it's the Tuesday of the week of reading day. Good, important distinction, yes. Homework grades posted on Relate. Yeah, eventually, but it'll be probably pretty close to when your final grade comes out, so I'm not sure if that matters to you or not. Okay, any other questions about presentations? The project grading is in the syllabus. If you have any questions about what any of that means, please let me know. And I can tell you, you want to make sure you have all those components, because even like a really good project might be missing some things that are pretty important for the final grade. So things like Git contribution, stuff like that. So making sure you can get all the points that you need. All right, I think that's pretty much it. So today we're going to have 2 micro lectures on machine learning. So there's 2 different takes on that, and we're also going to have a lecture on research, so doing research in the department, I guess outside the department, how to get involved with that. All right, so yeah, let's go ahead and get started.
Thank you, Logan. So, hello again, my name is Duke, I teach the data science hackerspace, and today I was talking to you about machine learning without the hype. This is very different from the lecture I gave during hackerspace, so these are entirely disjoint. You need to be hard data in hackerspace to understand this, and please don't leave if you did do hackerspace, because this is, again, new material. So let's start this off with relevant XKCD. Machine learning is a massive linear algebra. Yes. So you put data in one side, pass it through a bunch of linear algebra math, and then on the other side you get back answers. And if your answers aren't exactly what you would hope they would be, you just stir around this linear algebra a little bit, run it through again. Hopefully it's better this time. And this is, for the most part, accurate. This is the model that we'll be using in today's lecture. We're not going to assume at all that you know anything about linear algebra or calculus or anything like that. We're just going to say you have a system that takes in some input, does computations on it, gives you back an output. All right, so our agenda today is to briefly cover machine learning, especially machine learning theory, in about 30 minutes. We're going to go over some introduction and definitions. This is the same as in hackerspace. And then talk about representation, optimization, and generalization, which are the 3 main challenges of machine learning. Okay, so start with some definitions. It is the field of AI where predictions are made based on data. So what I mean by this is that AI traditionally has been the field of building systems that act like people would. Now, in the past, in the 60s, 70s, and a bit into the 80s, machine learning wasn't present yet. It was mostly called rule-based systems. And And so rule-based systems would have a set of rules programmed in by humans, and it would act according to those rules. So basically a series of handmade if statements. This is, of course, not scalable, and so scientists created this concept called machine learning, which takes in data, passes it through some mess of math, and then returns out some action or some classification or some output of the other. So it builds some model that is parameterized by a set of parameters, and it avoids statically programmed behavior. So as someone who's doing machine learning, you would not have to be writing as much code as someone who's doing software engineering or systems or anything like that, which is honestly a huge draw to the field. But the question is, what does it mean to learn from data? Machine learning is a field of AI, which means that it's something that perceives an environment and takes actions to achieve a set of goals. For instance, these minions from, I think, Lee, it might be Dota, I'm not sure, but are these minions an example of AI? According to this definition, does it perceive its environment and take actions to achieve those goals? What is I remember the thing? Let's get some answers here. All right, spend silence, I like that. Minions are questionably AI. So it definitely takes some actions to achieve its goals. That's clear, it's attacking this playable character right here. So it definitely is taking actions to achieve the goal of capturing the tower. But it is not machine learning because it does not actually learn from data. These minions operate according to some set of rules, and so it's not actually learning from the data that it observes. All right, so two main classes of machine learning. We have unsupervised and supervised. Unsupervised machine learning learns patterns between data points and doesn't require a human to actively tell it how to label points. So these are things like word embeddings, recommender systems, which is what you find in Netflix, in Amazon, Spotify, and ad engines. There are things like clustering models that try to cluster together points, and image compression, where you try to create some small numerical vector that represents an image. And so these are things that a human doesn't need to interact with. It's just a black box you throw onto some data set and it learns some useful information about that data set. On the other hand, you have supervised machine learning, which learns to label data points according to a human's guidance. These are things like, given a stock market, predict whether or not some share is going to go up or down in price. For Bitcoin, it's very easy right now. Things like image classification. So, given this image, classify that it is a picture of baseball as opposed to, say, football or hockey. Things like object detection. So, detecting that this is a baseball player. This is a baseball player from probably a different team. And so on and so forth. That's object detection. And speaker identification. So, given a lecturer's voice, determine which person it is from a list of known people. And so you'll notice that these are very closely related to how a human learns, or like a human has tasks. So with things like unsupervised learning, it's like how a child learns to recognize that all of these things that look like separate objects are actually the same kind of object, and a child doesn't need an adult to tell it that these objects are similar. Whereas with supervised learning, that's like saying a child looks at an object, and an adult tells them this is, say, a car, or a horse, or a dog, or whatever. And so they can learn to label this object in the future. We can treat training machine learning algorithms as like training a small child to perform a task, in that it requires a lot of training data, and occasionally requires some tweaking here and there to get the results. So in general, the problem statement is, given a training set of examples X and labeled Y, learn a model that predicts Y given X. So going back to the example from before, if you were given the image recognition task, this might be given a small image, 32 by 32 image, classify what kind of object it is. So here, X is the space of training examples, so images, and Y is the space of creating labels. So your classes of like a dog or a cat or a horse or whatever. And Machine learning assumes that both the training and the prediction data are drawn from some distribution D that is the same for both training and prediction. So it assumes that whatever tasks you give it to train on, you're going to give it a fair test of that in testing. So, for instance, take this class. It's very reasonable for us to give you some task of create a Python program that solves some problem. And we will test you on this later by giving you Python problems which you're supposed to code up. And ideally, these problems are kind of the same kinds of problems. This is problems being drawn from the same distribution. If we were to give you an unfair task, is we teach you problems in Python that ask you to answer questions on exams that are in, say, C++. Probably you're going to do a lot worse on the C++ problems than you would do in the Python problems. And that's a mismatch between training and prediction. Machine learning assumes that these two are the same. So we're giving a fair test. Most models are represented by some set of parameters theta that are trained. And that's what it means by learning from data, is that it adjusts these parameters theta in order to do well on the test. First of all, we talk about representation. Representation evaluates whether or not a model can approximately represent the training data. And so different architectures can represent different amounts of information depending on how expressive they are. Okay. So most ML algorithms in common use are known as universal function approximators, which means they can represent anything you want. And just to get like a little bit of sense of what representation means in this context, let's talk about programming. So let's say you had something that was a bunch of if statements, and you want to see how representative these if statements are. Okay, what can you represent with a single if statement? You can represent any set of two things. If some condition is true, then label this as a dog, otherwise label it as a cat. So there's not very much representation power here. You can only represent any set of two things. Now what if you're given two if statements? Like you can nest if statements 2 layers deep. Then you can label more things. Actually exponentially more, you can label 4 things. These from your first if statement, you branch off. And so you'd be like, if this thing has 4 legs, and this thing has a snout, then it's a dog. If this thing has 4 legs and it has pointy ears, then it's a cat. If this thing has 2 legs and pointy ears, then it's an elf. If this thing has 2 legs and a snout, then it's a werewolf, whatever. Right, so the more if statements you have, the more representative your function class is. If you have arbitrarily many if statements, you can now represent arbitrarily many things. But now, it's a bit troubling that everything we use can represent arbitrary functions. And we'll see why this is a problem. So, a universal function approximator is a class of functions f, where we can find a function in this function class that is close to any other function. Here we call it g. So, for example, let's say we have the function class of all linear functions. So, any linear function, you want to see whether or not this is a universal function approximator. And so, let's say we give you some function that was a quadratic, so y equals x squared. No linear function can represent this well. As you go, keep increasing or decreasing x, eventually x squared and any linear function of x will be very, very different. So we say that linear functions cannot represent quadratic functions. Now, contrast this with the set of all polynomials. So let's say we gave you the ability to use any polynomial you want and told you to represent an arbitrary function. Those of you who've taken calculus will know that this is definitely possible by using something called the Maclaurin or Taylor series. So you can represent any function as some quadratic, as some polynomial with infinitely many terms. And so we say that the class of all polynomials is a universal function approximator because it can represent any function. Does anyone have any questions so far? I know this is a very new concept. No questions. So next, why is this a desirable property? This is desirable because there is an unknown function f star that maps every x that you can see to its correct label. This guarantee. And so if we have a universal function approximator as our model, then we're guaranteed to be able to find some model that is good enough at approximating f star. So if we can approximate f star, this means we can label every training example we see according to its correct label. Or more philosophically, this f star might be a human looking at these examples and then labeling them. And so this is saying, if we can represent any function, then we can represent this human who's looking at these data examples with a complicated enough function. And so this gets you into like interesting territory of how close can we get to representing a human brain or human cognition just using a function. Next, we'll talk about how to measure whether a model is doing well or it's doing poorly. This is something called risk, which is a numerical measurement of how poorly a model performs. Population risk measures how poorly the model performs on average for all possible samples that the model might see. So the way this is done is you can draw a sample x, y from your distribution, then you measure how badly this model does, which is this loss function. So this is a loss function that is applied to your function. Okay, so I did the notation bit wrong. So essentially, you're given an example x and its label y. Take the function you've learned called f, predict what label y should be, and then you'll get a loss, which is like how badly this model does compared to the true label. And the loss is the expectation over all possible samples you can see of this loss. So, in other words, it's the expected value of how badly it's going to do if you just gave it a random sample. Now, for example, this might be you give it a random 32 by 32 image and you ask it to predict what's in this image. And the population risk is how badly you expect it to perform for any image you might give it. Now, of course, this is impossible to minimize exactly because your population might be infinitely large. There's exponentially many images that you can draw, and it's not possible to minimize the risk exactly over all of those, or even measure that. So we use something instead called empirical risk. Empirical risk measures how poorly the model performs with a set of data that it can see. So what we do is we have a training set of size m, and then we look at the average loss that this model gets over the training examples that we show. So we're trying to minimize the average, which is like 1 over m times the sum. That's just the average, the numerical mean of the loss that it gets for these training examples and the training labels it's supposed to have. You can show that the empirical risk is an unbiased estimator of the true population risk. So things that have low empirical risk, so things that perform well on the data that you show it, will tend to perform well on the data that it hasn't seen before. Any questions before we move on? No questions. Next is optimization, which is the way that we minimize risk for machine learning models. So optimization explores how to find the best set of parameters to fit data that is measured by the empirical risk. Note that I said before, we can't minimize the population risk exactly, so we have to minimize the empirical risk instead. And so what this does, in general, is that it starts out with an initial guess, and then iteratively improves towards a local minimum of risk. So we start out by just having a heap of linear algebra that is just a random mess of lineage. And then this has some set of parameters, and then as you keep running your model, you will slowly move those parameters towards something that's more sensible. So stirring the pot until your parameters actually make sense, and you predict things that are reasonable. The standard algorithm for solving optimization is known as stochastic gradient descent, or SGD. Now, SGD is an algorithm for minimizing any function where you know the derivatives. In machine learning, there's a model they're trying to train, as well as a loss function that should be minimized for the population risk, but you don't know the true gradient for the entire population. You can't find the gradient for your parameters compared to all possible images you might see, and so you have to stochastically or randomly estimate its gradient. And so we see here an example of stochastic gradient descent, where this is the point of high loss, highlighted in red. This blue point is the minimum where you're trying to get to. So this has high risk, this has low risk. And so you take steps going downhill to that risk. Yes?
How do you ensure that, because it looks like you can discuss that it's a local minimum and not find like the best?
Yes, that's definitely a valid point. Stochastic gradient descent can get stuck in a local minimum. And depending on who you ask, this happens either a lot or a little. The best way to fix this is to start out in a bunch of different points, rerun your model, and hopefully one of them will find the true minimum. There's not really a better way.
Does this work with both supervised and unsupervised?
Yes, so it's just that this works with any function that you're trying to minimize. So if you were to take this and go back to your Algebra 1 class and try to minimize a parabola, you can descend the gradient of that as well, get the lowest point for that parabola. And so the function L they're trying to minimize, this L is just different depending on whether you're doing supervised or unsupervised learning, but you have function L regardless. And so as long as you have this function L that has some sort of derivatives, you can minimize that. And then lastly, I see Kabir is back there in the audience. Make sure he gets a chance to spot. But we're going to talk about generalization, which is the difference between the empirical and population risk. So now that you've trained a model with optimization that performs well on your training data, how well is this model going to perform on real-world data that you might see? And so the intuition is that models that generalize well are more useful and safer to use. So consider, for instance, a model that is trained to drive a car. If this model generalizes well, it's going to perform well regardless of what road conditions it's put into or what vehicles are around it. If a model that doesn't generalize well, it's not going to do well in more circumstances. It's just going to do well on the very few circumstances that it has already seen. So we want good generalization as well as good optimization. And a failure to generalize is called overfitting. This means that a model memorizes its training set, but doesn't actually learn the real mapping F star. In our figure right here, this is overfitting. We have a set of blue points above this parabola, and a set of red points below this parabola. And you can see that this black line, I don't know how split the screen is, but you might be able to see this black line that shows F star. And it's a bit noisy. But this parabola in general represents the data you're trying to lead. Now, this green line is a model that has overfitted. And so you'll notice that it labels each point correctly. So it has optimized well. It labels everything on either above it if it's blue or below it if it's red. And so it has optimized well. It does well on training data. But this is not what you want to learn because it's jagged, it's unsafe. You might have things that are almost on the border that it labels incorrectly. And so this model generalizes very poorly. And there are several tools for measuring generalization. This is a very active area of research. But the most classical way of measuring generalization is using VC dimension. VC dimension, or Vatanenko dimension, is a measurement of the flexibility of model class. And it's defined as the largest set of points that can be shattered or arbitrarily labeled by this model class. Just to give you some intuition, because this is a rather odd concept, VC dimension is a measurement of how flexible a model is. And so here we see things that, on the left we have a linear classifier. This has low VC dimension. So it's not very flexible. Given the set of points, blue on the top, red on the bottom, it can only approximately find that boundary. It's not going to do especially well. This is called underfitting. Things with too low VC dimensions will underfit. So it doesn't learn this well at all. Next, we have something that has adequate VC dimension. So it's supposed to learn a parabola. You can see that it's approximately a parabola here. And something that has just right VC dimension will label things well and learn a sensible boundary. This boundary is sensible. It captures mostly the blue points on one side, red points on the other, and it ignores outliers. This is the best case scenario. On the other hand, you have something that is over-parameterized. This thing has overfitted. It has too high of VC dimension. It's too flexible. And so if you have something that's too flexible, it's going to perform exactly perfectly on training data, but it's going to perform badly on real-world data. See here, there are pockets of red where this is probably just outliers.
Yeah, is this dimension at all related to how many data parameters you chose?
Yes. So the student was asking about whether VC dimension is related to the number of parameters you have, and it is. So think back to the pile of lineage analogies. And so, like, the loosest bounds on VC dimension and on generalization are based on parameter count. So, intuitively, a neural net that has more parameters has a higher VC dimension than a neural net with fewer parameters. And so, you can think about this in terms of just like interpolation. If you've worked with that at all in numerical methods, like if you have 2 points, you can draw a line through it, and it has 2 parameters. It has the slope and the intercept. If you have 3 points, you can draw a parabola. And the parabola has parameters A, B, and C, for like ax squared plus bx plus c. If you have 4 points, you can draw a cubic through it, and that has 4 free parameters. And so this is like really hand-wavy, but like you can generalize this to neural networks as well. And so the more parameters you have, the higher VC dimension it has. And so you can use factorization terms. VC dimension is kind of a bad thing because VC dimension measures how many points you can shadow. So how many points you can arbitrarily label. And arbitrarily labeling means that it can fit these things perfectly, and you don't know why it's fitting. A popular failure case of machine learning is where you take real-world examples and you give it fake labels. So you just arbitrarily call images by random labels. So you have pictures of horses, you call them ships. You have pictures of dogs, you call them trucks, whatever, and you do this entirely randomly. And a neural network will still learn to predict it perfectly. If you have a big enough neural network, like most of the ones in practice today, and you give it a training set that is labeled arbitrarily and entirely randomly, it will still do perfectly. And so this is a big problem. And I think there's a paper on it called like Understanding Deep Learning Requires Rethinking Generalization that came out a few years ago. So this is a big problem. If you want to get into ML theory, this is probably the most exciting area at the moment. Like optimization was solved 20 years ago, approximately. Generalization is really big nowadays, and it probably will be for the near future. So just a quick recap, if I'm running out of time. Today we talked about machine learning. Machine learning learns to assign predictions based on the data that it's seen. We talked about three things. Representation is how well a function class can represent data. Optimization is how one trains the model to minimize risk on the data that it's allowed to see. Hold on, I'll take questions in a moment. And generalization is how well a trained model will perform on the real world and on data that it hasn't already seen. Any questions? I know you had a question. Please speak up. I'm sorry, I can't hear you. Oh, yes. That's bad because it means that this model can just like memorize training examples. And so think of it as a CS student in CS 421. Right? I'm going to rag on that because I'm taking a class right now. It's in that class, it's entirely possible. So the way the class works is that you're given a practice exam on some topic and also a weekly quiz on that topic. And these two things are exactly the same. Now, there's two kinds of students in the class. One kind of student actually learns the material and can actually understand what a compiler is, and then solves the problem in the exam context. The other kind of student memorizes the answer to that particular question beforehand, and then just types that really quick in 5 minutes and then leaves. Right? In this analogy, both students have performed perfectly, and you can't tell these two students apart based on the test score. And so if you train a model that performs perfectly well on your training data, you don't know whether it's actually learned the function you want it to learn, or it's just learned to memorize noise. Yes, and so if you have a model that you can give it random noise, and it can memorize that random noise, that means that you trained a model that can just memorize data examples. And you don't want that. You don't want something that just like memorizes examples. You want something that actually learns the underlying function. Okay, any other questions? All right, thank you for your time.
This on? Oh, fantastic. Okay, so while Michael sets up, I'll give you a quick intro. We'll do our best to get you guys out of here. What, 8 o'clock? Yeah, something like that. Yeah, so actually going right off the end of what Duke was saying, we're going to be talking a little bit about regularization. So that's, how do you, what can you do in this world of sort of deep learning that's sort of getting away from us. And we're a little bit more focused on classical methods, so linear regression, that sort of stuff. What can you do in terms of like controlling the VC dimension as one thing, but sort of controlling the way that your model learns and what it learns, so that you can actually ask it to learn reasonable functions that make some amount of sense. Full disclosure, these slides were initially developed a bit ago, and might have a little bit extra math, but it's nice to go through, and we'll do our best to have it make sense. Okay, yeah. Quick show of hands, have you guys talked about linear regression? I know one hackerspace maybe did. Okay. So we're going to be sort of talking about like a probabilistic perspective on linear regression and why linear regression is what it is, and then sort of regularization. So I'm Kabir.
I'm Michael. both juniors in CS. So we're going to be talking about interpreting linear regression from a Bayesian perspective, and I don't know how many stats classes you guys have taken, but in general, when people say like they're looking at something from a Bayesian perspective, or they're being a Bayesian or something, that means that they're treating these population parameters that you're trying to learn as random variables themselves, and so that allows you to learn in different ways and make different assumptions. So the other kind of common approach, which is not as common anymore, I guess, is frequentist. But like I said, we're going to look at linear regression from a Bayesian perspective.
So linear regression that you guys sort of may have talked about a little bit is you know, they have these set of points that represent, you know, maybe this is like on your X you've got like location or like some like something that's like what? Oh yeah, foot size and like correlated to height, or sort of the first one that got. One of the really interesting ones that you see a lot is like closeness to like particular landmarks and like housing prices, and sort of what you're trying to do is sort of learn that relationship. And you know, in this case, it looks like it's kind of a linear relationship, and you've got these sort of, you know, these two lines that you consider lines of best fit. Which of these lines sort of represents the trend that we're seeing here? And sort of just by eyeballing it, the difference between these two lines is non-obvious. And sort of your instinct might be, oh, the first one actually looks like most of the points are closer to the line. But if you actually, you know, apply sort of ordinary least squares regression, what you end up seeing is it's actually the second line of best fit that's a better representation of this data. And sort of the question that arises from that is, how do we define, or how do we know when we've done a good job? What is a good line of best fit?
And kind of going back to what Duke was saying earlier, one of these concepts that we deal with in order to solve this problem is called regularization. Pretty much means you insert some extra information into your problem, or add some priors to your parameters or something to make so that your problem is easier to solve and generalizes better. So if you look at that interpolation, actually, which Duke referenced earlier, you see that there's two models that can fit this data perfectly, but the simpler model tends to be better. And so we want to try to get that green line instead of the blue line. And so we're going to talk about ways of inserting information into our models so that we can generate these more generalizable, better models. Okay, so it's going to start to get a little bit more mathy. But anyways, we define a residual as just the difference between what we predict, which is just the weight matrix times the input, and then subtract the true label y. And so in order to do ordinary least squares regression, we assume that these errors are distributed according to a Gaussian distribution, or normal model, normal distribution. You guys have probably seen this before. What is that standard bell curve? And so we set the mean to be 0 because we want the average of all of our errors to be 0. We want roughly the same number of points below our line of best fit and the same as the number of points above our line of best fit. And so the second plot is just that residual plot, so you can see exactly how those residuals are with respect to the actual line of best fit, the predictions. Okay, so the goal of optimizing this model or learning this model is to find the parameters that maximize the likelihood of this model. So when people say the likelihood of a model, like the likelihood of some theta or set of parameters, in this case we're using W, given our data, is the same thing as saying the probability of observing our data given the parameters. And so that's what that's saying up there. Saying MLE, maximum likelihood estimate, of W hat equals the maximum over our arguments of the joint probability of all of our residuals. And And then, so joint prob, I don't know how much that you guys have done, but generally a joint probability is just probability of observing all of those things. So, for example, if we had we were predicting 3 points, we had 3 residuals, it just be the probability that those residuals were what we measured them to be. Okay, good. Okay, so here's another kind of regularization that we add. We assume that these errors are independent from each other. So that means that when we find the residual for a given data point, that has no effect on the probability of observing a residual for another data point. And so what that allows us to do is separate this joint probability into just a series or a product of the individual probabilities. And so you can rephrase that joint probability, like I said, as just that product. And then, next slide. Yeah, so from the previous slide, we assumed these residuals were Gaussian. So I just rephrase that, and then PDF, which describes the probability of observing a specific value in that distribution, is just what is written up there. You guys don't need to memorize that or anything like that. I mean, everyone has to look it up every time, for the most part. And so those two, the second to top line and the third to top line are the exact same thing. But then I also ask the question, why? Like, why do people tend to use the Gaussian assumption on the residuals? And so people do use different distributions, but in general, the normal distribution and the Gaussian distribution tends to work really well because it's a thing called the central limit theorem, which in the basic case says that if you have the sum of IID distributions, meaning independent and identically distributed, that sum is going to be Gaussian, as the number of variables goes to infinity. And so when we think of our error, the error is what we can't model using just this linear regression. And so it's a reasonable assumption to say that that error is just the sum of a bunch of random effects that we're not paying attention to. And so because it's a sum of a bunch of random effects, we can roughly approximate it using Gaussian. And so, so because we're doing an argmax, we can drop any constant coefficient across this product. So the normalization constant out in front of that, like the first term and then in each term of the product, we can just drop it. And then the next step, we can take the log, because if the log function is convex, and so it won't change what value we get when we take an argmax of the parameters. If that doesn't make any sense, it's okay. But people tend to do this all the time in optimization, because summations, once you take the log, you can separate that product into just summations. They're algebraically the same, and so it makes computing it much simpler. So once we take the log, then we reverse the negative, and so now instead of doing an argmax for the parameters, we're doing an argmin, and we get rid of that extra constant coefficient at the bottom, q sigma squared, and so we're just left with minimizing the squared error. And so that's why every time you hear people talk about the line of best fit and the ordinary of these squares, they're just minimizing the square residuals, the sum of the residual squared.
Yeah, so like we said, there's a little bit of extra math here, but if you're really trying to take away sort of the key points from this, it's, we have interest in fitting some line of best fit, and there's two things that we need to do in order to make that feasible at all. One is this assumption of independence of errors, right? Just to simplify the optimization that we're doing, and it's kind of a reasonable assumption. We don't expect the errors that we have between samples to be correlated. And then sort of the assumption that our residuals are normally distributed is sort of another assumption you can make to sort of simplify the optimization. And once you're in a form like this, you can either use a closed form solution that they've come up with, or the stuff that Duke was talking about, right? We've switched from a maximization to a minimization, and so anything like SGD can actually be used to solve any of these optimization problems.
So this is roughly saying the same thing, but like I said, people could make different assumptions on the distribution of those residuals. And so this is just a case where instead of making a Gaussian assumption, we're making a Laplacian assumption, which is just another distribution that's actually very closely related to Gaussian, but instead of having a square in the exponent, you just have an absolute value. And so that just results in a different optimization and therefore a different model when you're done training. But it roughly works out to the same thing, to a very similar final equation. Alright, so back to this idea of simplicity, the kind of rule of thumb or name that people call this is Occam's razor, which means generally the simpler your model is, the better it is, as long as it's still performed well. And so I plotted just a quadratic function with some Gaussian noise. So here I know that the error is actually distributed according to Gaussian. And then I just fit regular ordinary least squares, except I augmented it so it can learn a quadratic as well. But you see, if we just do ordinary least squares, we get this kind of curvy line that isn't the function that I plotted. And so the problem that we're trying to tackle is how can we modify this model so that we get a simpler line of this fit that makes more sense and actually fits the data better. And so what this second model actually is called regression. You guys will probably learn about it when you take ML class or stats class. It's the same thing as ordinary least squared regression, except we penalize the norm of the weights. So the larger the weights are, the worse our loss increases as the norm of our weights increases. And so when we're optimizing this, our model will try to keep the weights small. Or if we keep our weights small, then we'll have a simpler model. And so in this case, we're using squared 2, which is not really super relevant yet. And so again, this is just the same equation, except now instead of doing maximum likelihood estimation, we're doing, it's called maximum a posteriori, which is just the same thing, the joint probability of the residuals, but now we're also considering the probability of the weights as well. So if you notice the last term up there is just W, so we're trying to model that probability as well. And so we make the same assumptions, roughly. And so all the math pretty much works out the same, except now, because we've assumed that our weights are distributed according to a Gaussian, we get that final term again, which is the simpler loss function that you'll usually see when you're training a regression.
And again, connecting it back a little bit to what Duke was talking about, if you look at sort of what this ridge regression term is doing, going back to Duke had sort of a more pronounced example of this in one of his slides when we were talking about sort of the ability of your model to shatter a set of data. What this regularization term ends up doing is penalizing your model when you start to come up with boundaries that are sort of those wild boundaries that sort of aren't fit to functions and sort of make sense. You've got like some parameters that are sort of way out of line with the other ones. Those are going to be penalized more heavily. And that's going to get you, again, so here you see the smoothness and sort of going back to sort of Duke's slides, there you also saw that same smoothness, sort of less complex models.
Oh, great. So just a brief summary of what we've gone over so far. We have a little bit more to go over, but ordinary least squares, it's just assumes Gaussian distribution of the residuals, and we don't deal with the probability of the weights themselves. And ridge regression is just like ordinary least squares regression. We have a Gaussian distribution of the residuals, but now we also have a probability associated with the weights, or prior. Okay, so here's just another alternative. People call this Laceration regression. Very similar to ridge regression, except instead of now using a 2 norm on the weight matrix, we use a 1 norm. And so from a probabilistic perspective, that means that we're optimizing a different probability. And so here, for maybe people who aren't super familiar with these distributions. The orange is the Gaussian, and the blue is the Laplace. And so you can see that there's different probabilities of observing different x values at the bottom. And so this will have an effect on what your model ends up learning, what weights it ends up choosing. And time to kind of go back to order least squares to bring it full circle. Like I said, we're talking about this from a Bayesian perspective. In Bayesians, they like to think that their priors, or that the weights, are also distributed according to some distribution that we choose. And so in lasso regression and grid regression, we saw that these weights are distributed according to the Laplacian or Gaussian. But how can we try to apply that back to just regular order least squares regression? So it turns out that if you assume an uninformative prior or a uniform prior, meaning your weights are distributed according to a uniform distribution, if you maximize that, if you use maximum a posteriori, then it ends up being the same thing as NO. So here we just worked the exact same math again, except the exact same math as the second slide, except now we have the probability of the weights in here, and we're assuming it's distributed according to a uniform distribution. But because that distribution is uniform, the probability of observing any set of weights is the same. And so, like I said before, because we're doing argmax, we can drop constants. And so we just drop that constant, and our final form ends up being the same as our previous exposure to OSR.
Yeah, so again, really what regularization allows us to do is simplify our models and sort of inject our own prior knowledge of the system and of the function that we're optimizing. If we know that particular sets of data or particular interpretations of the data are prone to failure in certain ways, be that from overfitting, be that from underfitting, or a particular kind of overfitting, we can use things like regression to sort of, use things like regularization to sort of control the functions that our models learn. And we can analyze things that sort of just get thrown around in the ML world, especially now that everyone's like, drop a neural network on it, or pull out sklearn and just try whatever works or whatever gives you the right output. So we can control those things using things like, by understanding sort of the uniform prior that ordinary least squares assumes, we're sort of controlling that prior either in a Gaussian or Laplace way, and sort of getting reasonable looking outputs. Yeah, that's all we have. So questions? Otherwise, I think you're free to go. Yeah, you're free to go. Oh, JK, you're not free to go. They have stuff for you.
Okay, so we're going to have our last micro lecture on participating in research. So if you can come down. Okay, and just while we're waiting, another quick announcement. Remember that there's an extra credit homework due next week. So you don't have to do it, it's extra credit. We'll have a little bit of office hours, but you can check to see when those will be. But yeah, just wanted to let you guys know. Okay. Okay, so this is Vishal with our research micro lecture.
Hey guys, actually signed up for Vishal, and I'm sort of talking about my experience with research on campus. So before I begin, I'm just going to sort of give you an overview of where I research and sort of like what they do there. I research at the Healthcare Engineering Systems Center, which basically means they work on a lot of virtual reality simulation type projects related to healthcare, right? So for example, some of the projects is like simulating robotic surgery in virtual reality, or like, doing different procedures in virtual reality, right? And so the way it works is there's this one, head professor, his name is Dr. Casey Dawson, I can't pronounce his first name, sorry. But, and he really goes around, talks to different companies, secures money for different projects, and sort of like doles out all the work. And then, layer below that is the PhD students, obviously, do their postdoc work. And the thing is, like, a lot of these people are really specialized in one area. So, for example, over the summer, I worked with a postdoc who was building using something called the Raven 2 surgical robot and using haptic force feedback and computer vision, sort of create a robot that doctors can use as the next iteration after Da Vinci. And the thing is that he has all this knowledge about mechanical and mechanical engineering and the physics related to this robot, but it's not really worth his time to go in and try to learn how to make this simulator in VR, because one of the things is it's pretty hard to use a surgical robot, especially even if you're a doctor, you have to learn to use all these different mechanisms and stuff. And the best way to do it is sort of create a simulation environment where you can use demos and different modules to learn. And so what he asked me to do was, take the model of the robot, they already have the prefabs for it and whatnot, and put it in virtual reality. And with virtual reality, use these haptic controllers that he was using for the actual robot for surgeons to use, and in turn, try to code in the physics and the inverse kinematics to make it work. And so, like, I throw around a lot of words in there, but in reality, my job is sort of to tie in all these different parts of the project. And so, specifically, the project I want to talk about is this project that Mayo Clinic has given our research sort of group. And essentially, this project is that there's a lot of cancer patients and patients of other chronic diseases. Their treatment is extremely nuanced and complex. It's not straightforward. You can't just Google, what do I do in this situation? For example, if a patient, because they're taking their meds one day, or they forget some sort of nuance, and the next day they have all these questions. And instead of going to a doctor, what Mayo and OSF sort of wanted to do is that this patient who's entering their data in this sort of platform, they should use analytics and computation stuff, so that they can tell this patient what to do. And sort of what my job was is that, again, I should build a virtual doctor office, essentially, right? And then in this virtual doctor's office, I have to code a doctor one. And the one component was making sure the doctor looked realistic, has real facial expressions, sort of like you're interacting with the doctor. And two, make sure that this doctor is able to talk to this patient in simplified terms, not in super complex medical terminology and stuff like that. And so there was another group of researchers a few years before me working on this project, which the whole idea with the project was to take this whole bank of medical terminology, medical terms, medical phrases, and sort of simplify it for the average person, layman like us. And so it's sort of trying to find this middle ground where it's a very basic question that you can Google and a very specific question that requires your doctor to know everything about you. And it sort of takes all the questions in between and tries to solve, try to find a way in order that this patient doesn't actually need to talk or reach the doctor. And so right now the project's in the proposal phase, we just got funding for it. But there's a lot of components to it in reality. And so as a student researcher, someone who's not dedicating their full time to this, they sort of assigned me the task of going through and sort of connecting all the different pieces of research that has been done before and making sure they all integrate and work together well. And so as a student, I find it really rewarding. The thing is, I came in, I had some virtual reality experience, but it takes a lot of knowledge to be able to build a full end-to-end sort of application that not only has, ML components using wavenet technology to make the person sound real, trying to incorporate communicate with the patient and sort of different analytics perspectives. And they never expected me to do each and any of those individual things on my own, especially since there's all these different postdocs and all these different professors that are working on this already. And so I would build demos and I would build different applications to show at different conferences and slowly building up that application. I know I sort of ran through the project. I guess mainly what I was asked to talk about is how I came about getting this research and sort of getting more involved in it going forward. And what I noticed is that I came on a campus as a freshman last year, and the summer before when I was visiting U of I, sort of understand what I wanted to do here, I already kind of knew that I wanted to do research, but I didn't really know where. It's kind of intimidating, UIUC is very renowned for its research, there's a lot of money that goes in here. I mean, as you can see, Siebel is a much nicer building than any of the LAS buildings, right? And so all these research areas have so much money flowing in. For example, in my building, there's maybe at least 15 Oculus Go's, at least another 5 or 6 these Steam VR devices. They have LG VR devices. They have all sorts of different devices. And so they're trying to sort of bring this new age of healthcare into virtual reality because that's where it's really applicable, because you can learn in sort of real time, right? And so I just happened to be this professor through a friend of a friend, and I just sort of talked to him. He said, I've been really looking for a lot of students to do this research for me, and I sort of realized that's a pattern across everywhere. Because there's a there's a lot of super specialized PhD and postdoc students, but there's not a lot of people to do sort of the grunt work and sort of the simple stuff, right? Like, you know, it's really easy to build, nowadays it's really easy to build something like an algorithm or something like that to talk to you in sort of natural language and make it sound like real. But for a lot of postdocs, you know, they're mainly focused on the hard stuff of the project, like doing stuff that's never been done before. And so I kept pestering him over the break, you know, over the summer, and I kept talking to him, and then he sort of said, okay, here, come on. And he gave me like a very simple project to start off with, very basic stuff. And, you know, I completed that semester, and I just kept talking to him, kept communicating with him, kept meeting different professors, kept meeting different people, and trying to sort of understand. And one of the most valuable pieces of experience that I've felt that I've gotten from research, you know, is that you guys are all like freshmen, right? So as freshmen, you sort of are, even if you've done CS 3, 4, 5 years before coming here, you started coding, you know, like 5th, 6th grade, whatever you guys were doing now, right? So we don't really know a lot about like the people who've been putting in work day by day, like, you know, keep trying to expand their repertoire and already, you know, done what we're going to be doing in college over the next 4 years. And sort of puts things in perspective for me. And it sort of shows you that, like, you can mature a lot faster as a student when you're seeing these people working on like high-level crazy stuff. For example, like the other day, I was just sitting down and having a conversation with my colleagues, and they were just discussing this math proof to sort of optimize how you choose the beginning weights for an LSTM, right, or an RNN or a CNN. And, you know, I never really thought about the way you would do that with the mathematical proof and stuff like that. And so I just sat there and I sort of saw their line of thinking, the way they approach the problem, and the way they see how they're going to build something like this. Because they sort of see the long term. For all of them, their projects are like, all right, let's do a 4-year project, and they build the pieces of the project incrementally. Right? And when you sort of see that without having sort of real-world experience working a job, like, I was able to see how a product is done from the bottom to the top, end to end, and I sort of saw what it takes to, you know, build something like this. And so I guess I sort of rambled on a little bit, but, you know, what I want people to take away from sort of what I'm talking about is that research is all about, like, it's really learning experience. I came in to research thinking I was, you know, hot stuff, thinking, you know, like, it can't be that crazy. Like, I've been coding for a long time. I know Java, I know C, like, no big deal. And it puts things in a lot of perspective. It sort of gives you direction of what you might want to do with your CS knowledge. It sort of gives you a different perspective on how to think of ideas and stuff like that. That'd be all.
Okay, guys, thanks for being here today. So a couple last things. The attendance form will be posted in the general Slack channel, and the code word for this week is Urbana. Also, you guys might be curious who won the meme contest. So if you're in the group for the physics simulation, the VR physics simulation, you're the winning group, so congratulations.